Let's talk then a little bit more about sequences of functions. And this I sort of trailed off at the end last time. I want to do properly what I failed to do properly last time. But we are talking about uniform convergence of sequences of functions. Uniform convergence of sequences of functions. I'll refresh our memory with the definition. So we say Fn converges to F uniformly on some domain A when, and that set A is important, right? Just like uniform convergence, uniform continuity, the particular set that you talk about makes a big difference. The sequence of functions converges uniformly on some set when, this is epsilon's kind of thing, for all epsilon greater than 0 there exists big N, a natural number, such that for all x in A, n greater than the big N implies Fn of x minus f of x less than epsilon. What you see here looks like the definition of convergence of a sequence. The only difference is that the things in a sequence, it would be xn. This is Fn of x. And this has to be true for all x in the domain sets that you're talking about. All right. And what this looks like on a picture means that all the function values are within epsilon of the thing that they are converging to. So for example, if I have functions which are converging to, well, the simplest version of the picture is if the functions are converging to 0, which is many of our functions have been. I don't want that thick line. So if this is f, which is the 0 function, it's just easiest to draw the picture if f is the 0 function. And my other functions look something like this. It means that eventually all values of the function on your domain are within epsilon of what they're approaching. So it sort of means like there's this little epsilon window here where actually it goes both ways as usual. All the values of the function are within this window of the function that they're approaching, which on this picture is 0. All right. When the function they're approaching is not 0, this picture looks slightly weirder. Like if the function was, say, y equals x that they're approaching, if that was the function f, then uniform convergence would look like all the other functions would sort of be super close to that. And maybe they could be on either side, right? If it's, they could just kind of flip back and forth. And then the epsilon neighborhoods would be something like everything is within this epsilon band, but measured in terms of distance away from what they're approaching, all right? In this case, the picture looks the easiest if they are approaching 0. But if they're approaching something else, it's still like a band away from that with radius epsilon. Although epsilon is measured, it's always measured vertically, not like perpendicular, not orthogonally to the thing, which makes it a little weirder, the picture. All right, anyway, this is what uniform convergence means on some set A. So for example, on 1 to infinity, 1 over nx converges to 0 uniformly. That's because, I'll do this on the picture and then we'll do the actual proof of this, but it's because, say, from 1 to infinity, that means I'm talking about this domain just to the right of the number 1. The limiting function is 0. And then what do all the other functions? 1 over x looks like this. 1 over 2x is half as big. 1 over 3x is a third as big, and so on. And it is true in this example that no matter what the epsilon is, eventually all of these functions, on this part of their domain at least, all of the functions, the entire functions will lie inside this this band, right? On this picture, some of them are outside, but if the n is large enough, eventually all of those graphs end up inside that horizontal strip, at least from 1 to infinity, all right? Whereas if I tried to do this on 0 to infinity, actually then it's not uniform anymore. So on 0 to infinity, it's not uniform. It still converges pointwise to 0 because at each individual point, the limit of those functions is going to 0. But it's not uniform on 0 to infinity because these functions, they all look like this. They all have this vertical asymptote, right? That means that they do not all eventually fit inside this band. Actually, all of them stretch outside the band at some point on their left side, right? They don't all fit inside the band here. Whereas this one, if we cut everything off at 1, then eventually all of them really do fit inside the band entirely. But if we go all the way to 0, actually none of them fit inside the band entirely. Yeah?
So for pointwise, like, it's like they get into it on the point, but like for uniform it has to be in it entirely.
Yeah, you could say that. Yeah, like for this one is not uniform. It's because like you can take this point. If you look near 0, there's always going to be some points above the line. Pointwise just means at any particular point, eventually that point gets below the line. But that's different from saying the entire graph is below the line. I think this is what you said.
Yeah.
Yep. Yeah, it's about point by point versus like the entire graph. All right, and as you can see, the precise choice of what this set is matters a lot. So in this case, for that set, the convergence is uniform. For this set, it is not. Actually, in this example, any set which doesn't try to cozy up right next to the asymptote. I chose 1 here, but I could have chose a half instead or anything like that, as long as you don't try to go all the way to 0. All right, let's try to actually prove this with the epsilons. And this is the part that I screwed up last time, because it was the very end. I was trying to get through it, and I got sloppy, and I messed it up. So let's try. So here's a real proof. Fn of x equals 1 over nx, and then I want to show that Fn converges to 0, that is the function 0, uniformly on the set 1 to infinity. That was the first picture that I drew up here. This says want to show WTS. It looks like WB. Not what I meant. WTS. All right. Let's see if we can do it. We got to do the epsilons thing. What I wrote last time was almost correct, but I messed it up in a very important way. So let's try and do it right this time. Anyway, this looks superficially like any old epsilons proof. You just have to make sure you do it correctly. So I'm going to begin with let epsilon greater than 0 be given. And then we'll find delta greater than 0 such that what I want is, first of all, for all x in 1 to infinity, n, it's not delta, sorry, it's the big N. This is a sequence. N greater than big N implies absolute value f n of x minus f of x less than epsilon. All right, where, the first thing we should do is try to simplify that thing to the right of the big arrow. This is Fn of x minus f of x, where Fn is the sequence of functions that I'm talking about. That would be 1 over nx. And f of x is the function that that they are approaching, which I'm taking to be just 0. So actually that's just this. And since x is from 1 to infinity, that's going to be positive, and so I can ignore the absolute value signs. All right. And I hope everyone's with it so far. Right here is where I messed up last time. Actually, what I wrote at this point was not wrong, but it was, I mean, it wasn't false, but it was just bad for the sake of this proof. Right here, I'm going to say less than 1 over n. This is since x is greater than 1. When you're doing this uniform business, the thing is the big N cannot depend on x. So when you're doing your simplifying here, you want to get rid of the x entirely by using either equal signs or less than or equals. All right. So this is this right here. I just forgot to do that last time, which messed me up for the whole rest of the thing. All right, but anyway, now we can proceed with like a usual sort of epsilon styles proof here. I would say we want this to be less than 0. So I want less than epsilon, I want 1 over n less than epsilon. So that means just rearranging. N has to be greater than 1 over epsilon. And so that's what I choose my big N to be. So I say let the big N be greater than 1 over epsilon. And then I just write the end of the proof. Then if n greater than big N, we have this equals 1 over nx, which is less than 1 over n, which is less than epsilon, right? This is 1 over, like this. All right. Sorry for messing that up last time. The important step for the sake of the uniform business is right there, when we can get rid of the x there. That is necessary because when you choose the big N is not allowed to depend on the x. All right. If you're doing pointwise convergence, then the big N can depend on the x, but for uniform, it must not. That's the whole difference between pointwise and uniform. Any thoughts about that one? All right, great. You can expect to do, you'll see some on a homework like this. Once you know what you're doing, these proofs are not all that difficult. All right. Can we look back at some of the other examples that we talked about were converging pointwise but not uniform? I just want to look at them, and I had a couple of other examples that we discussed for pointwise convergence. I want to go back and ask, do they really converge pointwise? Do they also converge uniformly? So here was another example. Fn of x equals x squared over n, right? These ones, if I were to draw them, the first one is just x squared, but the next one is x squared over 2, which is that same picture, but everything, the y value has been cut in half. So it's really sort of crunched down like that. This is x squared over 2. X squared over 3 looks like this, right? And so on. Like that. So here, Fn of x, can I just say pointwise? Can anybody say, does that converge to anything? Point by point? I think it does. We said so last time around. Last time we talked about this one. Anybody recall? Yeah? Yeah, 0. If you just think about, if you look at some particular value for x and then ask yourself, does this dividing by n, what happens to that as n goes to infinity? The answer is you get 0, right? So for a specific x value, you do get 0 when the n goes to infinity. So this here goes to 0 for all x, right? Pointwise. At each individual point, these sequence of functions does approach 0. Is the convergence uniform? So does Fn of x go to 0 uniformly let's say on R. That means considering the entire picture. So what it converges to is this, right? This is 0. Is the convergence uniform? What that means on all of R, uniform on all of R would mean for the entire thing, here's what it converges to, and then here's all the other ones, right? Is it true that eventually all of these functions, their entire graph falls within this little band here? I would say no. Can anyone explain why? I mean, obviously, these ones that I drew here, they stretch outside the band. But if you let the n get high enough, does the entire graph fall inside the band there?
Is it because, like, I don't know, since you have like a parabola, it's going to get like squishier, but it's still going to like be going up?
Yeah. These are going to be parabolas every time, right? They get squishier, as he said, but that's kind of like only in the middle, right? A parabola is still going up to infinity on either side. So no matter how much you squish it down at every stage here, these are all parabolas, which means eventually all of them will stretch outside this band. So the answer to this question, does it converge uniformly, is no. Because they are all parabolas, I'll say each Fn is a parabola. So none of them is, I will say, none of them is within epsilon of 0 on all of R, right? None of those functions actually is inside that band of epsilons when you consider it. Just the whole parabola, it's not, because it goes up to infinity on either end, even if it got squishy, right? We could think about other sets. How about the same function, but what about does Fn of x converge to 0 uniformly on, let's say, -1 to 1? So that means I only look here, and then I look at these functions, so that they are parabolas still, like this. And again, you know, they go to 0, right? And I'm thinking about this little strip here made by epsilons. What do you say if I'm only considering between -1 from -1 to 1 here? Is it true that these graphs all eventually fall within the band? I think now it is true. I mean, it's still true that these parabolas, they still go up to infinity, like over here, but just in this region here, actually they will all fall within this this narrow band, right? From minus epsilon to epsilon. And so the answer here is, does they converge here? The answer here is yes. All right. And this would not be so hard to prove, although I don't want to go through the details. I would like for you all to have like an intuitive notion, though, of what it means, at least on a picture, for the convergence to be uniform versus pointwise. All right. So it's not uniform on all of R. It is uniform just on that interval right there. In fact, I believe I would go so far as to say it's going to be uniform on any bounded interval, but if the interval that you're considering is unbounded, like if it goes all the way out to infinity, then it's not going to be uniform anymore. Because that's, if you really go all the way out to infinity, then those parabolas will eventually also go up to infinity, and so they will leave this little narrow strip. But if you confine it to any bounded interval, then they will not leave the strip. All right. Great. Just one more of the cute examples that we had looked at in the past. How about f of x, fn of x equals sine of x over n? I kind of like this example. It's a little weird. Sine of x over n. So when n equals 1, this is just ordinary sine of x, like that. When n is 2, this is sine of x over 2, which is that same thing, but stretch out in the x direction so that it looks like this instead. And then sine of x, so this is sine of x. This is sine of x over 2. Sine of x over 3 is stretched out like even further. They all still go up to 1 and down to -1, but we are stretching making longer and longer periods, as they say. All right. What does this converge to? Does anybody remember? We talked about this pointwise. It converges to 0. Yeah, this one also goes to 0. This is very strange in my opinion, but it is true. If x is any specific number, and you ask what happens here when the n goes to infinity, well, if x is a specific number, then x over n will go to 0, and then we'll get sine of 0, which is 0. So pointwise, this thing approaches 0. Pointwise, fn of x goes to 0. Does it converge uniformly? Let's just say on all of R. Is it converging uniformly? To 0. You know, 0, the thing it's converging to is like this, right? Is the convergence uniform? That is, if I draw a little band here, does the entire graph eventually fit inside the band? No way. Not at all, sir. Not remotely. I have a nephew who likes this phrase. Not remotely. He's like, he started saying this when he was like 8 years old. I thought it was funny. And I say that when I'm around him now. And at other times. Yeah, this is not converging uniformly because every one of these goes all the way up to 1 and all the way down to -1 eventually. They cannot stay in this little band, all right? Although, just like before, if you confine the domain to a closed interval, a bounded interval I mean, then actually it would converge uniformly, but not on all of R. So the answer is no. All right, but I'll just say, but on a bounded interval, it does converge uniformly. All right. Yes?
So for both of these examples, like the interval doesn't matter, it just has to be.
Yeah, it could be any interval, yeah, as long as it's bounded. Actually, this is a theorem that we are not going to get into just because it's the last week of class, but it is a fact that if you have functions which converge pointwise and the domain is a compact set, then automatically it's also uniform. So a bounded interval would be a compact set. Yeah. All right. So uniform convergence. I have one theorem about uniform convergence that I want to do, and that will do it for this little bit about uniform convergence. Next time we'll talk about something different. When the convergence is uniform, I will just say nice theorems are true when the convergence is uniform. My general impression is pointwise convergence doesn't really mean much to me because functions can converge pointwise even if the thing they're converging to is actually very different from what we started with. Like I would say this is an example like that. They converge pointwise to the blue line even though none of them individually looks anything like the blue line. This is very weird to me. Pointwise convergence is pretty weird, but uniform convergence, so I will say nice things are true when the convergence is uniform. When the convergence is pointwise, it's kind of like you still don't really know very much about the situation. But when the convergence is uniform, nice theorems are true. For example, I'm just going to write, there's a theorem that says if Fn is continuous, then F is continuous. This is true, but only if the convergence is uniform. Or, here's another one. If Fn is bounded, then F is bounded. Or something like, this is also true, if Fn is differentiable, then F is differentiable. All of these things are true, but they need uniformness. If it's not uniform, then it's kind of like all bets are off, and you really can't say very much at all if it converges only pointwise. But if it's also uniform, then you get all of these nice theorems. Actually, that one about differentiability is only true. You also need the derivative to be continuous, but whatever. And then I'll just say one more. I just wanted to say this word once during the semester, even though we're not really going to talk about it at all. Integrable. I don't know if you've seen this word before. Differentiable means the derivative exists. Integrable means the integral exists. Yeah, that's a word. You don't use this word in a calculus class because basically every function you've ever heard of in a calculus class is automatically integrable. But there are functions, weird functions, that are not integrable. Things like the Thomé function, or the function which is like 1 for rational numbers and 0 for irrational numbers. Weird stuff like that. Actually, those ones that I just said, they are integrable. But some weird functions like that are not integrable. So anyway, I don't know if you care about this. I thought I might want to use this word. If it's uniformly convergent, though, then functions which are integrable, the thing that they converge to is also integrable. And in fact, they have the same integral. This is something that did not happen there was a weird example we had with like triangles getting taller, where the integral of each one of them was equal to 1, but the integral of the limit was 0. That cannot happen under uniform convergence. All right. Basically, all the theorems you want to be true are only true if the convergence is uniform. And I want to specifically talk about this one here, and then I will just leave the rest of them for you to think about, if you want to think about them or not. All right. So let's do that. I want to write this out as an actual theorem. This may be the last big epsilons type theorem that we do. So don't shed a tear. This is a thrilling conclusion in that sense, because this one actually uses the epsilon. You've heard of the epsilon over 2 trick. This one uses an epsilon over 3. Can you believe it? You take something, epsilon over 2, you usually take one thing and you sort of split it into 2 parts and you make each part less than epsilon over 2. Can you imagine how you would do epsilon over 3? It's very similar, but you need 3 parts. Anyway, let's see how it works. So this says if Fn converges to F uniformly on some domain A, and the Fn are all continuous on A, then F is continuous on A. This is not true for pointwise convergence. We had an example e to the nx, where those are each continuous individually, but they converge to something which is discontinuous. If it's uniform, though, they always will end up being continuous. All right, let's see if we can do it. So here's our proof. I'm going to try to write. Let me try and draw a picture first, just to get us going here. Actually, I have to say a few words here. So I'm going to say take some point C in A, and then we'll show that F is continuous at C. All right. So that's what continuous on the whole set means, that at each point, I mean pointwise continuous on A. I'm not talking about uniform continuity, which is an extra, like a double uniform. I'm not into that. Not today, at least. So I'm going to show that F is continuous. So the picture you should have in mind is like, here's C, and continuous at C, i.e., of course, what that means is lim x goes to C, f of x equals f of C, right? That's what continuous at C means. So the picture that I'm going to draw involves C and then X, which is some other point close to C. And what we have, there's actually several functions in play here, right? We have F, which is the function that everything is approaching. And maybe just to make it simple, I'm going to draw that as if it were a straight line. This is the F. And of course, we have some values, right? F of X and also F of C. But then there's also the other functions in the sequence that are approaching F. They are, Fn. And maybe I'll just draw one of them. How about if I draw, maybe I'll draw a few of them. It could be, the first few could be sort of far away, right? But eventually you get down to a function which is quite close to that one. Something like that, right? This is like F1, F2, etc. And they are approaching F uniformly. It's not entirely clear. I'm gonna modify my picture a little bit, if you don't mind. This is still kind of far away. I wanted to draw this as if it was really quite close. Sorry about that. Remember, the uniformity means that eventually all the functions lie inside this little band, right? That's what uniformity indicates, at least on the domain A. All right. Okay. Anyway, this is the setup. All right. Do you really agree that F is continuous? Now, on my picture, I drew it like F is continuous, although we don't necessarily know that F is continuous. Maybe I shouldn't have drawn a nice straight line. How about put some little, sorry, I keep modifying my picture after the fact. We don't know ahead of time that it's continuous. But the thing is, we kind of know that this X has to be close to this point. There are some other points. F of X has to be close to that other point. And then this point, F of C, has to be close to this other point. And if the X and the C are close together, then those 2 points have to be close together. This is where the epsilon over 3 is going to come in. It's really sort of that, that, and that, and that, right? All three of those things have to be really close together. And that is going to make it so that these two original points have to be really close together. And that's what shows you that the F is actually continuous. That's the basic idea behind what the proof is going to look like. Anyway, let's see if we can do it. I will refer back to this picture every so often. Anyway, this is what I have to show, and that we need to show using the epsilon. So I'm going to say, let epsilon greater than 0 be given. This is proving, this is a nice little review for the test, I suppose. Proving something is continuous using the epsilons. We'll find delta greater than 0 such that x minus 0 less than x minus c less than delta implies f of x minus f of c less than epsilon. All right? This is how you show that something is continuous. We'll do epsilon over 3. Can you believe it? What I'm going to do is I'm going to split this thing into 3 pieces according to sort of these 3 things here. So I'm going to write f of x minus f of c as f of x. Okay, on my picture, f of x is close to this point on one of these things. I'll say fn of x. All right. That's the first little vertical distance there, the distance from f of x to fn of x, which is one of the functions in the sequence. All right. And then I'm going to say plus fn of x minus fn of c. This is the distance between here and here, at least in the y direction, the vertical distance between these 2 points, fn of x and fn of c. And then finally, I'm going to go from fn of c to f of c. That's this last vertical distance here, plus fn of c minus f of c. All right. the way that I wrote that, all those things in the middle cancel out, and so this is actually equal to f of x minus f of c. But I can split this apart. So this means that f of x minus f of c is less than or equal, doing the triangle inequality with my sort of three pieces like that. Absolute value, the first one, f of x minus fn of x, plus the second one, fn of x minus fn of c, plus the last one, fn of c minus f of c, right? And now, can we say, why must each of those three parts be really small? Is it true that we can make the first one smaller than anything? Well, if we choose the n large enough, then this can be made less than epsilon over 3 because fn's converge to f, right? So I can say, choosing n large enough and delta small enough, we can make, I have to tell you why each of these three parts can be less than epsilon over 3. So the first one, f of x minus fn of x, is less than epsilon over 3 since fn converges to f. On A, all right? If you choose the n large enough, that distance there between those two things will eventually be less than epsilon over 3. And I think for the same reason, it is also true for fn of c minus f of c, for the same reason. fn of c minus f of c can also be less than epsilon over 3. Again, it is important that it is uniform. Why is that? It's because I'm using the same n for both x and also for c. If the convergence is only pointwise, then you might need to use a different n for different points. And this is where the uniformness is important. Because the convergence is uniform, I can choose the same n, which will be large enough for both points. All right? And then what about the one in the middle? Why is this one less than epsilon over 3? fn of x minus fn of c less than epsilon over 3, since this one is because fn is continuous, which means that when you plug into this function, if x is approaching c, then this thing minus that other thing can be less than whatever you like. So this is true since fn is continuous. I'm not using the fact that f is continuous, that's what I'm trying to prove. But since fn is continuous, I can make that less than epsilon over 3. All right, those are the three little pieces. All right, and then so put it all together. So absolute value f of x minus f of c less than or equal to epsilon over 3. Well, it's really straight up less than epsilon over 3 plus epsilon over 3 plus epsilon over 3. All right. That's it. And I think maybe I'm going to leave it at that for today. I will make a little confession. This is sort of the proper end of the course as far as I consider it. So next time we will do another something which is going to be, I would say, less technical and more pictures. I don't know. Numbers, actually. Could you believe numbers? Yeah, that's something to look forward to next time around. It will be amazing. You will be able to impress your friends with the knowledge that you learn next time around. I think your friends will probably not be impressed by this, although I hope that you feel like it's interesting. See you next time.